First of all, I'd just like to thank you for the opportunity to present here today. So I'm going to give an overview of the way we do method development now in AstraZeneca within the development organisations compared to how we were doing it a couple of years ago, and hopefully sort of explain to you how we've been able to make our method development process more efficient through the use of in silico modelling. I'd also like to acknowledge that this isn't a presentation and work that's been solely done by me, so there's a number of people that's been involved with this, pulling this together, and also involved with how we progress our capability around method development. So, I mean, why is this important? Well, we've come to this point from a sustainability perspective and the impact that analytical science and analytical chemistry does have on the environment. Now, if you look at how much analytical science contributes to the environmental pollution, it is quite a major polluter in terms of some of the things that we do, and that mainly comes from the solvents that we use. You can see here that the costs to the environment around producing solvents, transporting solvents, and how we dispose of the waste that we produce as analytical scientists is one of the biggest contributors to the carbon dioxide output from analytical science as a whole. Now, globally, if you, I think someone looked at how much metric tons is produced, or how much CO2 is produced from the logistics of managing solvents, and it was 30 million metric tons. Now, this is a huge amount. If you put that into how many humans does 30 million metric tons represent, well, it's about, I think we said nearly half a million, 500 million humans. Sort of that's the equivalent weight of CO2 that we're putting into the environment every year. So when you think about it in that terms, it's a huge amount, and anything that we can do to reduce the amount of solvent consumption is really important. Thinking about water as well, water actually is a precious commodity, and what we need to do is really sort of be really respectful in how we use water, how we achieve pure water where we get our water from, but how we return that water to the environment in a pure state as well. So making sure that our analytical grade water is used responsibly is also really important, which is a big driver in how we can do our method development in a more sustainable way. Other ways that we might want to think about, just as from a liquid chromatography perspective, are the columns that we use and the columns that we burn through when we're doing method development generates waste, and it's something that we have to deal with. But also in the amount of sample preparation that we do in terms of the vials that we use, the filters that can be used in terms of sample prep, how we introduce our samples onto instruments through vials and caps. All of these things are really important, and often are single-use entities and consumables that essentially all need to be minimized as well in terms of how much we use when we're developing our methods. When we start to think about green chemistry and the impact that chemistry has on the environment, Paul Anastas was really the founder of this thinking around how we can be green in the sort of analytical chemistry that we do. And he proposed 12 key rules of green chemistry. And what Anastas said was, if you're hitting all of these individually at different levels in the work that you do, then you can probably say you're working in the greenest space, or moving to a green space in the delivery of chemistry and chemical sciences. What he also started to look at is pulling out some key interactions where analytical chemistry has got a particular element associated with his green rules of 12 green chemistry. And these are around trying to reduce the waste that we produce. So by reducing the waste, you're not having to get rid of much and put anything back into the environment that's harmful. Also, can we use feedstocks from renewable sources or biosources so that we're not having to make our solvents or make our reagents in an unsustainable way? Can we avoid derivatization using harmful chemicals and analyze the material as it's presented to us as analytical sciences? And also, can we make sure that we're doing everything in the safest possible way using the safest solvents? And by doing this, can we also start to look at how we can maximize the output from one given analysis? So can we make sure that it analyzes multiple things at one time? And also, is it possible to almost do your analysis at the point at which the sample is being generated? So, and also in real time, not having to transport samples to different places. So all of these really started to crystallize thinking around how we can, how as analytical scientists, we can think about doing our analysis in a greener way. Other areas that, where green analytical chemistry can be really important is take your analysis to the point of source. So field analysis in the field, so to speak, where the sample is being generated, whether that's at the plant where the sample is being produced, or literally in the field when it comes to environmental samples. Can you take your instrument to that point and do your analysis there? And this is where we started to think, well, how can we do our method development in a greener way? So can we move away from sort of looking at single methods and optimizing one point or one factor at a time? And can we move to more of a screening approach where we look at a wide space in a small number of experiments to really try and narrow down where we want to focus our efforts? And then once we know where we want to work, we use statistical and chemometric approaches to really understand the sort of the experimental space that we'll be working in. And aside from that, can we then also start to reduce the volumes of materials that we're making, so that we're not having a great impact on sample preparation? So these are some of the key easy wins that we can achieve as analytical sciences when we're trying to deliver sort of our method development strategies. And this is some of the areas that we've worked on over the last sort of, last 3 to 5 years at AstraZeneca. So this is about driving the work that we do and getting to the right first time mentality so that we're not wastefully repeating experiments that have failed for reasons that could otherwise been preventable. And where we are seeing a trend of analysis not being right first time, have we got structured problem solving measures in place to really allow us to understand what the root cause of that potential problem might be? And are we setting clear expectations on our scientists and our users of instruments about how they look after the instruments, how they're trained to use them, so that they understand the instruments well enough so that they can do basic troubleshooting, but not necessarily be super engineers in being able to fix everything? And then once we can start to, treat our instruments with care, we can look after them properly, we know what they're doing, can we start to reduce the number of physical experiments that we actually need to do to get that end result, and start to use the data that we're generating on a regular basis in more of an in silico, or in more of a way that allows us to model and simulate chromatographic separations. And I saw the results from the poll that was just up on the screen initially, and we've sort of done work in-house and shown that actually by using modelling and simulation as opposed to doing lots and lots of experiments, we can reduce the need for practical experimentation by somewhere in the region of 30 to 50%. So just to touch on what I'm going to sort of talk through now in a bit more detail is how we've historically done our method development and what we've done to drive to a more standard approach using modelling and simulation, using ACDLabs Perceptor and LC Simulator as tools that help us to deliver some of our modelling and simulation understanding. I also wanted to touch on how this aligns with some of the regulatory requirements that are now coming into play from the ICH group, and also how we've been able to remove a lot of the what we call essential waste activities. So these are activities that you have to do in order to get an end result, but actually don't really add any impact, any value to the work that you're doing. So how can we automate it so that we give our scientists more time to focus on the value-adding activities? And then finally, I'll just touch on where this leaves us in terms of robustness, ruggedness, and validation. So what we did historically when we were talking about method development, we had a method development workflow that could take in anything up to 30 working days. So if you think about that, that's actually about 6 weeks of a scientist's time to work through a development cycle. And this often relied on the scientists themselves focusing on or tweaking, something that they'd already been given. And a lot of it relied on extensive historical experience from the user or the scientist that was doing the work or that planned to do the work. This could be quicker in some cases, or it take longer depending on how complex or how critical that method was for the work that they're planning to do. And this really it resulted in a process that everybody approached slightly differently, and therefore it wasn't well defined. It was always applied inconsistently. People get to the end of it and have different endpoints. And like I said, there was a lot of work that went into doing low value but essential activities, but weren't having any significant impact. And when we looked at this, when we split this down into a typical development cycle, we actually saw that about 3/4 of the work we did was spent churning through the things that we had to do but weren't actually giving us any value. So these were things like transcribing instrument methods onto the instrument so that the instrument could run, manually searching through data and being able to process that manually and putting that manual transcription then into the statistical package or the modeling software itself. Whereas actually some of the high value, high impact work that was being missed was how you actually think about what experiments you needed to do within a sort of a design space that you might want to work in, or how you sort of go through and start making the real clear decisions based on the data that you've obtained. And what's happened recently within the regulatory environment is that the ICH group have released a new sort of guideline or a new procedure named Q14, and this is analytical procedure development. And this actually starts to talk about how you might be able to give yourself as an organization more benefit by understanding your methods in more detail. This idea that your analytical procedure or your analytical method that you're developing is there for the lifetime of a product. It's not just there for a moment in time. And actually, if you were able to understand that method in great detail through a series of enhanced development approaches, where you really get into the nitty-gritty and understand the relationships between the different parameters on the method that you're developing, you may start to be able to have a more simplistic ride from a regulatory perspective if you want to make changes in the future when your method becomes commercialized. So now that we've got some sort of background into what we were trying to do, we sat down and we revisited our method development workflow. And this is where we ended up with, in terms of, it's a sort of 8-step process. And it's really about split into sort of 3 main areas. So firstly, we want to really understand the project requirements that we're working to, and the sort of the method requirements that method or that procedure needs to operate at. And this is about understanding the analytes that you want to analyze for, where in the state of the development process that method is, or where it needs to be sort of amended or created. Is this very early in development within the pharmaceutical industry, for example, or is it nearing that commercial sort of facing method that is almost now fixed in stone to some degree? So how do we understand its key impact on where that method needs to do or operate in? And then the other thing that we then looked at is how can we simplify what the operator or the scientist or the analyst needs to do at the instrument? Where can we take away some of that pain where there's a lot of effort going into writing methods for the instrument, for example, rather than actually spending time thinking about what experiments you actually need to run. So how can we make those steps most efficient? So the next thing I'm going to just briefly touch on is each of the steps in a bit more detail. So each one of these 8 steps. So the first one starts with outlining what we call the analytical target profile, and this is something that's now been sort of rolled out through the ICH group in that Q14 procedure that I sort of alluded to a couple of slides ago. And this really defines the purpose of the method. So we sit down and we need to understand at what point in the development cycle is this method being produced, what does it need to do in terms of its job, and what does it need to actually analyze for. And once we sort of understand that information, and you can see the sort of the key bullet points on the left-hand side of the slide there, we then say, right, well, what are the method requirements to deliver the work in these areas? And we sit down and and this is all theoretical at this point. This is all sat down with a pen and a paper rather than doing anything sort of at the instrument. We'd look at what the critical quality attributes need to be of that method and what does that method need to analyze for. And we also go through a process of making sure that we get the right technique for the analytes that we're analyzing for. And for this, we need some knowledge of what the analytes are so that we can essentially put the right technique in place. And a key thing for the ATP, or the analytical target profile, is that we then make sure that we measure that how well that method performs throughout the life cycle for that while that method's being used. So if that, for instance, is a drug within the pharmaceutical industry, that method could be in use for 20, 30, 40 years. And what we want to do is make sure we've got the data to show how that method has performed in terms of its critical quality attributes over that lifetime, because that then helps us ensure that a method is suitable for its continued use. So once we've got the ATP documented, we then start to look at the analytes in a bit more detail, and we start to compile that physicochemical data. And for this, we found a lot of benefit from using Perceptor. That helps us predict not only the log D values of the known impurities, but also the pKa's where they've got a charge associated with them. And we're able to then look at this in terms of, well, how do we want to target our method development? Do we want to do a general screen that covers all pHs because we've got a lot of unknowns in there and we don't know the structures? Or actually, do we know what the structures are? And therefore, once we know what a structure is of some of the analytes that we need to look for, we can then say, right, well, actually, we want to target our method development so that we focus on a specific region of the pH range. So here's an example of 4 analytes, A, B, C, and D. And you can see here, once we put the structures into Perceptor and we're able to get the pKa's and the log D's, we could see that, for us, we might, on this example particularly, focusing on the low pH sort of screen of potential LC methods that we could run. If we were sort of expanding it and running it near neutral, it would probably give us some problems because there's a lot of change going on there in particular, analyte D and analyte A has got a change around the sort of near neutral mark. But also you could potentially use high pH in chromatography, but that has limitations around the stationary phases that you may have access to. So moving on, once we've got our physicochemical data through Perceptor, we can then start to see, right, well, what samples do we need to put into our method development? And this comes back again, looking at the ATP and deciding or understanding what your method is going to be needed for. So if it was a method that needed to show how stable something was over a long period of time, in the sense it needs to be stability indicated, you might want to put samples in there that have been force degraded so that you can see all of those key impurities. Equally, if we want to look at the isolated impurities or intermediates from a particular chemical process, and we're not so bothered about stability, we may only need to put samples in that have got isolated impurities or intermediates in there as part of that chemical assessment. If we're then looking at longer term use of this method over a period of time for different batches of the same material, we then may want to collate a selection of representative batches to do our method development. So all of this is about, again, really trying to understand what your method needs to do, focusing in on the right selection of samples to do that method development with, and not making things unnecessarily, again, from a sustainability perspective, to make your method development more focused. So I've mentioned a few times on some of the challenges we had around removing transcriptions, and this is one of the tools that we were able to develop when we were pulling this together, because one of the things that we found took a lot of time was scientists were putting lots of effort into creating a sequence of injections that would do flushes and washes and switch columns between different conditions. And actually what we said was, now that we understand what our physicochemical data is and what our where we need to either focus our screen or run a generic screen, we can then give a set sequence of injections with set methods that focus on a particular temperature gradient, pH, and all sort of run that in a very sort of standardized way, in the sense that we now have a single instrument that people can put their samples on. They can run those samples without too much effort in being able to create all of these methods in the background or sequences, and we do get a first pass result of data that they can look at and start to see, right, what is the most optimum area that I need to focus on next. This does require a dedicated instrument to run this, and this is where we've been able to sort of say what that instrument is capable of doing. So we have got a generic screen, and this is a screen where if you know, the scientist going through that ATP has a lot of unknowns in there. They have a lot of peaks. They don't understand the structures at this point. They may run the generic screen, which covers 4 columns initially on our LC system at 3 pHs. And then if they don't get any hits or positive progression from that point, they can then look at a second screen and expansion on that first one to look at 2 additional stationary phases, and again across the different pH values. Now, if we know that if we understand our structures of our analytes and we have looked at the log Ds and pKs, we can then say, right, we now, instead of doing that generic approach, we'll go through a targeted screen and either really narrow down straight away on the acidic, the near neutral, or the basic screen. And as I say, depending on what your physicochemical data tells you, that will inform what screen is the most appropriate. So I've said that this requires a specific instrument setup, and you can see here, this is the instrument setup that we have. So it needs to be an LC mass spec system that is capable of having 6 columns in some sort of column manager that can switch between any one. And it also has got the quaternary system in terms of the pump that allows us to pump from aqueous and then 2 solvent phases. But we've also put an extra valve on the D line within that allows us to then switch between different modifiers. So this really gives us a flexible sort of system that stands alone in doing method development screening for the scientists that need to have an understanding of how they want to progress. What you can see here is that first sort of generic screen where someone has decided, well, I don't really understand or know what my analytes are, so I'm just going to run that first pass screen, and that gives you 7 chromatograms initially. And from this, you can say, right, I can see visually what is the best chromatogram or what are the best conditions to go forward with. And because the instrument's got a mass spec on the end of it, it starts to really focus and understand its mass ions of each of the peaks on there, and it labels them accordingly. We've also got a more detailed report that focuses in on some of the good chromatographic performance characteristics. So have you got excessive tailing, or have you got reasonable resolution between critical peaks? And anything that doesn't really fit with that flashes up in red, so you can start to rule out some of the conditions. And finally, from the end of this, once it's done its processing, you end up with a table of key that gives you the key information. So it gives you your conditions that the sample was running, and the method that was operated. It gives you how many peaks were detected by that method, and then it gives you some information around tailing and resolution. And from this, you can start to understand what are the conditions that I then need to optimize in. Oh, so there's a few builds on here. So yeah, so that summarizes that. And the other table that this report gives you is then it starts to align what retention times each of the individual masses were detected at. And this is where it becomes really important, because this is another build that we were able to remove from that tedious process of doing this manually, trying to understand, right, well, where was peak 301, for instance, what retention time was this under all the different conditions, and we're able to get the chromatography data system to generate a report that gives us that information without too much effort from the scientists doing the work. Because once you've got that next stage, once you've focused on, right, I'm going to work at this pH, I'm going to work at this mobile phase, and at this potential pH, you can then go into a process of optimization. And this gives us our optimization sequence. So it allows us to focus in on a specific area that we've shown is looking like the most promising chromatography. And the sequence that runs will then run one of those samples or a number of those samples at different gradients, at different pHs and at different temperatures. And the report that comes out at the end allows us to make that transcription of all that data, all that information that comes out of the chromatography data system over into the LC simulator. So this is just an example of the sequence it would run. So you can see there it runs at 3 different temperatures and at 3 different gradients in this case. And sometimes we may put a second pH in there as well, just to see how that sort of impacts the separation. And from the report that's generated, we're able to export that information. And it's this LC simulator file converter that we've developed in-house. So this allows us to get the information ordered into and all the peaks tracked from their mass that allows us to then simply import that into the LC simulator sort of software package. And we've also got all of because this is run on, well, I said we've actually got 2 or 3 instruments that do this on a regular basis. So depending on what instrument you're using to develop your method, we've got all the instrument characteristics in the background as well. Dwell volume and all those sorts of things. So by putting all of this information in a structured way from the outset through the export and the import into LC Simulator, we've removed a whole host of manual transcriptions and time that the scientists would have spent manually entering this data historically. And now we can simply move on to how do we optimize this gradient to give us separation in the most robust and rugged way. And so once we've got that information, we then simply go through we've had some instances where if you've only got a few number of analytes, we will then click the button that says optimize this method in LC Simulator, and it gives us a set of conditions that we then would go and run practically and see how that behaves. Or if it's a bit more complex and there's a lot of peaks in there that need to achieve a certain resolution, we would sit there and work out, or the scientists would then use their intellect to really optimize their gradient. So once we've got to that optimized point, we then say, right, what does this look like in practice? And you can see there that this is a real example where the model gave us a particular chromatogram at the bottom there that we said would be acceptable in this case. And then we did a confirmatory injection, and the difference between the modeled version from LC Simulator and the actual was very small in terms, it was in the area of a few seconds difference in terms of the retention in some cases. So this was a real sort of good example where we're able to achieve a really sort of a good outcome from the structured way in the way we generated this data. So finally, once we've done our optimization, we would then go through the process of understanding robustness of the method. So how does that method work in terms of its continuing to meet the expected performance during routine and normal use? And we can do this by sort of varying slightly different things, or getting a different scientist to have a go at doing this, running this in a different lab within the organization. or we can also make some deliberate sort of slight changes and see whether or not that actually changes things to any extent. We would also look at ruggedness, and this is the key bit now in going back to the ICH Q14 statement around trying to understand some of the interactions between, you know, the different conditions and different parameters within the chromatographic method. And finally, once we believe we've got a method that's both robust and rugged, we would only then go into the full validation package to then say, we're going to put this through the validation and demonstrate that it's actually going to achieve what we need it to achieve on a day-to-day basis, and allow it to be used to help deliver the control strategy for the particular analyte that we're using. So just some final thoughts. I think when we think about using modelling and simulation, what we want to do is reduce the amount of experimentation we need to do, but also reduce the amount of waste we create and reduce the amount of samples we need to make. And that way we start to really move to a more sustainable future. We're always going to need some practical experimentation, because you need to do that in order to build your model. But it's about doing that in a very structured and organised way to keep those number of experiments to the smallest number possible. And one of the final things is about, once you've generated this data is really valuable. It shouldn't just be for this moment in time. You should then think about where you can use this in the future. And one of the things we look at now is how we can keep this model live and we can keep evolving it, so that if we do have to make changes in the future to that method, we've got a model that we can start with and almost use that in the first instance to see and predict where other impurities that, you know, suddenly appear as they do through development may elute.